Okay, so welcome to our discussion for GATE preparation, solving previous year GATE questions and some additional questions to build our concepts. Okay, so today we will discuss soil mechanics. So two previous questions, previous year GATE questions we will be discussing will deal with calculation of bulk density using our void ratio, water content, specific gravity. And second question will be calculation of effective pressure. And additionally, we will discuss questions to related with soil classification and also effect of capillary in the effective stress. Okay, so let's start. First question, GATE 2008, question number 78. The ground condition at a site are shown in figure below. The saturated unit weight of sand is kilonewton per meter cube. We have to calculate, and the water table is given to us. It is at the ground level. Water content is 20%. Specific gravity of solids is 2.7. Unit weight of water, we can take it as 10 kilonewton per meter cube. The reference material for the related question is cited below. To solve this question, we need to see that we have to calculate saturated unit weight of sand, which is weight of solids plus weight of water divided by total volume. Simply going through formula, what we can observe is gamma sat is nothing but gamma bulk in this case, because our water content, that is 20%, corresponds to saturation water content. Right? And gamma bulk can be written as gamma dry into 1 plus water content. Formula for gamma dry, that is dry bulk density, is simple enough. Gamma W into G divided by 1 plus E, where E is the void ratio. From the information given to us, that is saturation is 100% since the soil is below water table, the water content is 20%, and the specific gravity of solids is 2.7. We can use the formula, that is SE is equal to WG, where the symbols mean their usual terms, and we can calculate the value of E. So the easy way to remember this formula is sewage or Sehwag, whichever you feel like is comfortable for you. So when we multiply water content with the specific gravity, so 20% into 2.7, and divide by the saturation, that is saturation percentage, that is 100%, we get the value of void ratio as 0.54. Now when we substitute this value into our dry bulk density gamma D, we get gamma B is equal to 10 into 2.7 divided by 1.54 into 1 plus W, that is 1.2. When we solve this question, this expression, we will get gamma B is equal to approximately 21 kilonewton per meter cube. So that is the third option, which is correct. Okay, so this is how we can solve this question. The next question is going to be linked with this question, so it is a two-part question. So let's solve the second question. A GATE 2008 question number 79. The ground condition at a site are shown in the figure below. The total pressure, pore water pressure, effective stress at point P are respectively. So in this question, we are given that the water table is at the ground level. Water content of soil is 20%, and this is corresponding to saturation. So the degree of saturation is 100%. Specific gravity of solid is 2.7, that is the capital G. Unit weight of water is 10, that is gamma W. And we are asked what is the total stress, what is the pore water pressure, and what is the effective stress at a point which is 5 meters below the ground surface. Okay, so for this we need to calculate first, since the soil is saturated above this point, so we have to calculate gamma sat, which is actually the success, no, the question before this question, that is GATE 2008 question number 78. So we will directly apply that formula and calculate it here. That is gamma B is equal to gamma D 1 plus W, and gamma D is nothing but G gamma W 1 plus E. E we can calculate using the formula that relates the degree of saturation and the water content and the void ratio with specific gravity of solids. So 20 multiplied by 2.7 divided by 100, we get 0.54. And substituting this into our question, we get the bulk density, or in this case the saturation density of this soil as 21 kilonewton per meter cube. Okay, now we have to draw our stress diagram. So we have, this is, let's say this is the soil, this is the point, or this is the plane where we want to find out the stress, that is xx, and water level is at the soil surface, and this distance is 5 meters. So the total stress will be from water as well as from the solids. It is calculated using the bulk density, in this case saturation unit weight. So it will be gamma sat into 5, that is the depth. We denote it as sigma t. So it is 21 into 5, that is 105 kilonewton per meter square. Okay. Water stress represented as U is gamma W, unit weight of water, into depth, that is 10 into 5, 50 kilonewton per meter square. And the effective stress is nothing but the difference between these two. So total stress minus pore water pressure or water stress, that is 105 minus 50 is equal to 55 kilonewton per meter square. So you can clearly see that the correct answer for this question is option C. So we could have avoided all these extra calculations if we just saw that in no other option are we getting the value of total stress as 105, and we can save some time using these kind of tricks in the main exam. Okay. So these were the two questions for our quota to complete our GATE previous year quota. Now let's discuss some more questions, some more interesting questions related to soil classification, and one more question dealing with the capillary effect for the water stress. Oh, sorry, for the effective stress. Okay. So first question, this is related to the classification of sands or gravels. So if the coefficient of uniformity and coefficient of curvature of sand is found to be 7.5 and 2.5 respectively, as per the IS sand classification, IS classification, what is this classification for this sand? So we are given that this is a sand and the coefficient of uniformity, if you remember, that is Cu, and the formula for that is D60 by D10, right? And coefficient of curvature, that is Cc, that is D30 whole square divided by D60 into D10, right? So D60, D10, we can just say dx is size corresponding to x% finer, right? So we are given that Cu is 7.5 and Cc is 2.5. So what is this sand going to be classified as? Is it poorly graded gravel, poorly graded sand, well graded sand, or well graded gravel? So first of all, we can move out these options of gravel because in question itself we are given that it is sand, right? So whether it is poorly graded or well graded, how do we identify that? So if you remember, whenever we were given classification of sand or coarse material, we have to see that if it is sand, then the coefficient of uniformity, that is Cu, should be greater than 6 and Cc should fall in the range 1 to 3. And if it is gravel, then Cu should be greater than 4 and Cc should fall again between 1 and 3. Since it is sand, we will see whether Cu, that is coefficient of uniformity, is greater than 6. So we are given 7.5, which is greater than 6. So this condition is satisfied. Cc, the coefficient of curvature, is 2.5, that is in between 1 and 3. So this condition is also satisfied. So we know that it is well graded. And since in the question it is given that it is sand, so it is well graded sand. So the answer will be SW. Okay. See, in this question, instead of giving this sand directly, what else can be given is they can say that 10% or like 60% of the soil passed through 4.57 mm sieve and 40% was retained on that. So in that case, you have to remember that 4.75 is the maximum size of sand, and after that it is you know gravel. So that also can be used. In this case, if they give this information, then you have to remember that what is the size boundary for gravel, sand, clay, silt, and all those things, and you have to decide which soil is in this is the category belonging to. Okay, let's go to the next question. So this is the question where we are going to see the effect of capillary on the effective stress. So the water table in a certain area is at a depth of 4 meter below the ground surface. To a depth of 12 meter, the soil consists of very fine sand having the average void ratio of 0.7. Above the water table, the sand has an average degree of saturation of 50%. What will be the increase in the effective pressure in kilonewton per meter square on the horizontal plane at a depth 10 meter below the ground surface if the soil gets saturated by capillary up to a height of 1 meter above the water table? Okay, so let's draw and see what is the question asking us. So let's say this is the ground surface. 4 meter below we see water table. So 4 meter below we see water table. Okay. And till 12 meter below the ground surface we have a sand where the void ratio for this sand is 0.7. Okay. And above the water table we see that the degree of saturation is 50%. So S is 50% above the water table, and what will be S below the water table? It will be 100%. Okay. And what is asked of us? Okay, and also the specific density or the specific gravity of solids is given to us, that is G, that is 2.65. Okay. We are asked what is the stress or what is the change in the effective stress at a location which is 10 meter from the ground surface when the water table or the water rises by 1 meter in this sand due to the effect of capillary. So what we will do here, we will calculate the effective stress in both the cases and let's see what is the answer we get. So you see there will be a little bit difference in the from the conventional approach because it is mentioned clearly that the water is rising through capillary. So the pore water pressure is going to change. So we'll see that through our pressure diagram or the stress diagram. Okay. So first let's draw for the normal case. So let me just make it here 1 and we'll draw for the normal case. So let's draw the total stress first. For the total stress above the groundwater table, the total stress will be given by the bulk density into the height. So gamma b 1 into 4, right? And below the groundwater table, it will be given by the saturated unit weight or the saturated density. That will be gamma sat, or we can just say gamma b2 into 6. So this is the total stress. Okay, let me move these things. What about water stress? Water stress will start from the water table with value of gamma W into 6. And then the effective stress is nothing but the subtraction of these two values. And at this point, at the point at 10 meter below the ground. Now let me copy this and we'll paste it in another page and we'll see what happens in the second case. Okay, so this was the first case. Let us keep this also here. In the second case, the water level has moved 1 meter above. Okay, so the soil is not dry till 4 meters now. It is only dry till 3 meters. So the gamma B1 can only be used for the first 3 meters. To calculate the total stress, gamma B1 can only be used for the first 3 meters, right? And after that, since it is all filled with water, the pores are filled with water, the value will be given by gamma B2, which is nothing but the saturation unit weight, and that will be into 7 because the total height is 10 meters. Okay, now how the water stress will be affected? So if you remember, water is in tension under capillary, right? So the water above the groundwater table and in between in the capillary range is going to be uh, suffering from tension, means it is going to exert a negative force. So it will again start from 0 only at the groundwater table. So from our depth 4 to 10, it is again going to be gamma W into 6. But above that, from depth 3 to depth 4, that is the capillary range, for now, this water pressure, pore water pressure is going to be negative and it is going to be most negative at the top of the capillary fringe. That is going to be -1 into gamma W. 1 because the capillary depth is 1 meter. Okay. The thing is, this is not going to affect. So the pore water pressure at 10 meter, the pore water pressure at 10 meter is not going to change. It is just again going to be gamma W into 6 only. But the total stress has changed and that is going to change our effective stress. So let's calculate. Before we calculate, let's go above and calculate our gamma B1 and gamma B2. Okay. So For gamma B1, we need water content, and we can get water content again using our formula. SE is equal to WG. Water content is going to be 0.5 into 0.7 divided by 2.65, and it is equal to 13.2%. So I'll just write in decimals 1.32, 0.132. And gamma B1 is equal to 1.132 into 2.67 into 9.81 divided by 1.7. So this expression, this is for dry density. And when you solve this, you are going to get your gamma B1 as 17.31 kilonewton per meter cube. Okay. Gamma B2, for that we need to again calculate the water content below the groundwater table. That will be corresponding to S is equal to 100%. So we can just say that it is going to be twice that of the water content earlier. So it is going to be 0.264, right, 26.4%. And correspondingly our gamma B2 is going to be 1.264 into 2.67 into 9.81 divided by 1.7. So this value is coming out to be 19.32 kilonewton per meter cube, right? Just remember these values. We are going to use these values in the formula below. Okay. So let's solve. So sigma T, that is 4 into gamma B1 plus gamma B2 into 6. 4 into 17.31 plus 6 into, or let's write it in order, 19.32 into 6. So this value is coming out to be, let's just write here sigma T. We'll only calculate once when we are calculating our effective stress. So this is your sigma T. And what is your pore water pressure U? That is gamma W into 6. So U is nothing but 9.81 into 6. And sigma 1 dash, that is the effective stress, is going to be equal to gamma T minus U, and you can calculate. The final answer that you are going to get is 126.3 kilonewton per meter square. So you can go ahead and do this calculation and check whether you are getting the same answer or not. Okay, so this is first case. In second case, sigma T, as we said, pore water pressure is not going to be affected. So U is again 9.81 into 6, right, kilonewton per meter square. See, if you have doubt that pore water pressure, why it is not affected, it should be affected. See, remember that we are talking about stress, which is the value of this particular side of the triangle, the base of the triangle. If we were talking about the total force applied by water on this particular plane, then in that case we have to take the area, and in that case the negative area or the minus capillary, because of the capillary fringe, the tension in the water, the pore water pressure, that would have reduced the total force. But we are talking about stress, so it is not going to change. Okay, so the U is going to be same. Sigma T is going to be 3 into gamma B1 plus 7 into gamma B2. So we have 3 into 17.31 plus 7 into 19.32, right? And then we have sigma 2 dash, that is sigma T. Let me just write here also 2, 2 and 1, 1. Yeah, sigma T2 minus U, sigma 2 dash will come out to be 128.32 kilonewton per meter square. And what is asked of us? We are asked what is the difference or what is the rise in the effective stress, that is delta sigma dash, that is sigma 2 dash minus sigma 1 dash, and it is nothing but 2.02 kilonewton per meter square. So this is the answer. Okay. Sometimes in these questions there are also like some questions are there where they will say that ignore the effect of capillarity on water stress. In that case, you have to ignore the negative suction. It is the negative stress, negative pore water pressure that is occurring. So in that case, the answer is going to change if they are asking about the stress in the capillary range within this 3 to 4 meter depth. Otherwise, the answer is not going to change. Okay. Okay. Let's go to our final question for today. It is again a question, very good question related to our soil classification. So first we saw the soil classification for sand, coarse sand, fine sand. Now we are going to see soil classification for clay soil or fine sand, fine soil. Sieve analysis on a dry soil sample of mass 800 gram showed that 680 grams and 500 grams of the soil passed through 4.75 mm and 0.075 mm sieve size, respectively. The Casagrande experiment performed on the soil sample gave the following results. So we are given the water content and we are giving the number of blows in which the trench that we make in the Casagrande apparatus after putting the soil, the number of blows in which this trench is closed, that is given to us, and the water content corresponding to this particular soil. Okay. And what else is given? We are also given the water content at which the same soil sample, when rolled into a thread of diameter 3 meter, is broken. So we are given that water content at which we can roll the soil sample into a thread of diameter 3 mm. Okay, so using these two, you should immediately think that okay, we are given some information related to liquid limit and plastic limit. And as a matter of fact, if you look at it carefully, you see that we are given the water content corresponding to 25 blows, and we are given the water content corresponding to the 3 mm dia of our thread. So we are clearly given the liquid limit, that is 28%, and the plastic limit, that is 20%. Okay, so we are given these two. These two we can quickly identify. Now, whether the soil is we have been given some grain size distribution. So let's see. Let's first draw the soil size distribution chart itself. So 4.75 mm is the boundary, right? After this is gravel and cobble and boulder. So we are not going to worry about that. Okay, we can just write that from 4.75 to 80 mm we have gravel, and after that we have other things like cobble and boulders and all. So from 4.75 mm to 0.075 mm we have sand. I'm not going to go into fine sand, coarse sand and medium sand. This is sand from 0.75 mm to 4.75 mm. From 0.75 mm to 0.002 mm or 2 micron. From 0.075 mm to 0.002 mm, that is 2 micrometers, we have our silt, and below that we have clay. Okay. Okay, so let's see under which region does our majority of soil lies. So what we see here is that 680 grams passed through 4.75. So out of 800, 680 grams is finer than 4.75. So definitely it's going to be sand, silt or clay. But out of this 680 grams, 500 grams is finer than 0.075 mm. So you see, out of the 800, 500 is finer than 0.075 mm. So it is clearly either clay or silt, because 500 by 80, sorry, 500 by 800 into 100, it is definitely greater than 50%. So majority of our soil is either clay or silt. So it is going to be either M, or M for the silt, or C for clay, right? So let's look at our liquid limit and our plastic limit. Liquid limit is given to us as 28. So we can use the size chart, for to make our life easy for the classification. So if you remember that we have a size chart where we are given the volume or the plasticity index on the y-axis and the liquid limit on the x-axis, and we have a line which is often called as A line, right? What is the equation of that line? That line actually gives us the plasticity index, and it is given as 0.73 into liquid limit minus 20. So you calculate your plasticity index, and then you calculate the value of plasticity index that is coming from this formula. And if it is more, so if the point of your soil, if your soil is lying above this A line, then we call it as clay, and if the point is lying below this clay line, we call it as silt, right? So we can calculate that. And also we have a boundary at 50 percentage liquid limit. So if the liquid limit is more than 50 percentage, we call it as a highly compressible soil, and if it is below 50 percentage, we call it as a low compressible soil. So you can see that this classification is going to be, in here it is going to be Cl, low compressible clay, it is going to be Ch, highly compressible clay, it's going to be Mh, highly compressible silt, and going to be Ml, low compressible silt. And in this region, when you come across between more than liquid limit more than 10 and less than 20, you come across a region where you have a low compressible clay plus silt, Cl plus Ml. So that occurs when your plasticity index is between 4% and 7%. So let's see if we are safe, or we have to look at this kind of combination. So our liquid limit is 28, so definitely it is low compressible, right? And the plastic limit is 20. So the plasticity index in our case is 8%. And the one which we calculate from the formula is 0.73 into 28 minus 20. So it is 0.73 into 8. So the IP from this formula is lower than the value that we are actually getting. So our point for this particular soil is going to be above the A line. So this is the A line, and we are going to be above the A line, and luckily our plasticity index is not between 4 and 7, so we don't have to deal with the mixture of clay and silt. So we are somewhere, let's say we are somewhere here. So this is clay soil with low compressibility, right? So option 2 is the correct answer. Okay, so I hope you are able to follow and see how we are doing this kind of classification. So some no more questions, just a little bit changing the values. These type of questions are very common in GATE, and you can easily solve these questions if you just remember few of these equations. So this A line equation, for instance, 0.73 into liquid limit minus 20, right? And this liquid limit, sorry, plasticity index boundary, that is 4 when it is between 4 and 7, then you have to write it as a mixture of clay, silty clay soil, right? Like that. And this grain size distribution chart, that is definitely a must when we are dealing with soil classification. So 4.75 is the threshold, and after that, usually we don't get the grain size distribution above 4.75, because then it is just gravel and cobble. So usually the questions are not framed with that big of a size distribution. So you need to remember that from 4.75 to 0.075 mm we have sand, and the threshold between the clay and silt is 2 micrometers or 0.002 mm, whichever is comfortable for you. See, this question was a very good question because we this question combined the theory of Casagrande apparatus, plastic limit, and the normal grain size distribution. Right, so it's a very good refresher question. Okay, so that's all for today. So we are finishing the session early for the soil mechanics, and next week we have our transportation engineering. So that will be on the normal time on Sunday from 6 to 7, and let's meet and discuss transportation engineering. Thank you.